Last time we have studied the division algorithm. Now we shall see some problems. This is the problem set 2.2 from the book. The first problem we shall consider is show that any integer or square of any integer can be written in the form form 3k or 3k plus 1. Now we shall solve this problem. We know that if an integer is divided by 2, then the possible remainders are 0 or 1. If an integer is divided by 3, the possible remainders are 0 or 1 or 2, and so on. If it is divided by 4, the remainders will be 0, 1 or 3, 2, 3 or 3. And in general, if it is divided by m, the possible remainders will be 0, 1, 2 up to m minus 1. And thus we shall consider an integer. Any integer divided by 3 gives the remainders 0, 1 or 2. Therefore, any integer can be written. If it is divisible by 3, then it is of the form 3q. If it gives remainder 1 after division by 3, then it is of the form 3q plus 1. And if it gives remainder 2 after division by 3, then it is of the form 3q plus 2. So thus any integer can be written in the form of 3q or 3q plus 1 or 3q plus 2. You may try considering any integer divided by 3 and you will get it is of either of the form 3q, etc. Now we shall write like this. Any integer on division by 3 is of the form 3q or 3q plus 1 or 3q plus 2. So thus any integer is of the form either of these three forms. Now we shall show its square. What is the form of its square? Now 3q, suppose the integer is of the form 3q, all the multiples of 3. Then its square is 9q square. And we can write 9q square as 3 into 3q square. Or now this is of the form 3k, where k is 3q square. Further, next 3q plus 1, square of 3q plus 1. So it is 9q square plus 6q plus 1. We check this. And now we can write this as 3 common in bracket from these two. So it is 3q square, 2q, yes, it is 3q square plus 2q and plus 1 separate. And you see this can be taken as k. So therefore this is of the form 3k plus 1, where k is equal to 3q square plus 2q. All are integers. So q is integer, its square and multiple addition, subtraction, etc. will be integer. We name here it as k. Here we have considered this as k. Now what is the remaining third form is 3q plus 1, 3q plus 2. Now see what is its square. Its square will be 9q square plus 6 into 12 q and plus 2 square is 4. Now this can be written as 9q square plus 12q plus 3 plus 1. We split 4 as 3 plus 1. And now from these take 3 common. So this is 3 times 3q square plus 4q plus 1 plus 1. Or again, this is of the same form, 3k plus 1, where k is this bracket, 3q square plus 4q plus 1. So thus every integer is of this form, 3q or 3q plus 1 or 3q plus 2, and its square is either of the form 3k or 3k plus 1. Here it is also 3k plus 1. So this proves that square of any integer is of the form 3k plus 1. Now for example, we may consider 7. What is the 7 square? 7 square is 49. And which form is this one? 3k or 3k plus 1? Only two forms, 3k or 3k. Is it divisible by 3? No. And therefore we shall consider this as 48 plus 1. And this now can be written as 3k means 3 into 16 plus 1. So it is of form 3k plus 1. Now if you consider another number, say 9 square. Now 9 square is obviously 81, and that is 3 into 27. So it is of the form 3. We check like this. Consider any integer and check its square is of the form 3k or 3k plus 1. So this is the problem. Now you should see the solved problems in the book, that is on page 18 and 19, and try to solve the remaining problems from the exercise. Now we shall go to next part, that is greatest common divisor. So this also we have studied at high school level, greatest common divisor. So before going to greatest common divisor, we shall first define divisibility, and we write it as a definition for divisibility. If a and b are two integers, we say a divides b, or we say b is divisible by a. And condition is a not equal to 0. If there exists an integer c such that b is equal to a into c, and we write this as b is divisible by a. This we write as a divides b. Now if b there are different ways of saying this. A divides b, or b is divisible by a, or a is factor of b. We say a divides b, or a is factor of b, a is a factor of b, or b is a multiple of a. So this is the definition of divisibility. When one integer is divisible by another integer, when b is divisible by a, we can write b is equal to a into some other integer. Then we say b is divisible by a, or we say, we write it this as a divides b. A divides b, vertical bar, not oblique. So you must note this is not a by b or a oblique b, not like this. It is a divides b, vertical bar is there, and these two are different. Here a divides b. So or a is factor of b, or b is a multiple of a. In case b is not divisible by a, we write a does not divide b. In case b is not divisible by a. Now this is a simple concept. Examples. Say 3 divides 15. 3 divides 15 because since we can write by definition, you see b is divisible by, or you see this definition, b, a divides b, b is equal to ac. So here a is 3, b is 15, and we can write 15 as 3 into some integer, and that integer we know as 5. Or likewise 4 divides minus 24. The relation may be for positive integers or negative integers. 4 divides minus 24, since minus 24 is written as 4 into minus 6. So here c is minus 4, and so on. But we may see here 5 does not divide 12, because we can't write 12 is equal to 5 into some integer. So that is the relation between two integers. One integer divides the other integer, and we can't say 0 divides any integer. So we cannot say 0 divides say some any integer, or 0 divides 2, because this 2 cannot be written as 2 is equal to 0 into some integer. That is not possible, because 0 into any integer becomes 0. So therefore 0 does not divide any integer. So that is to be remembered. Now we shall consider some properties of this divisibility relation as a theorem. Theorem number 2. Now we should write the statement of the theorem. Theorem 2. See, the statement is like this. For integers ABC, we have the following results. The following results hold. The following holds. These are simple results depending only on the definition. First is a divides 0, 1 divides a divides a. Second, a divides 1 if and only a is equal to plus or minus 1. If a divides b and c divides d, then a into c divides b into d. We shall list these results and then we shall see the proof. If d divides b, a divides b, it is. If a divides b and b divides c, then a divides c. A divides b and B divides A, if and only if A is equal to plus or minus B. If A divides B and B is not 0, then mod A less than or equal to mod B. And finally, if A divides B and A divides C, then A divides bx plus cy for arbitrary integers x and y. So these are some results, and these results are to be proved using only the definition of a divisibility relation. So how we have defined divisibility? A divides B. You remember that. So all the results are to be proved using the definition. So we know A divides B. So this implies there exists an integer C such that this right side integer B is written as in terms of multiple of A into C for some C. So this is the definition. B is equal to A into C. Now see, the first two are obvious, you can prove it. Or see, A divides 0 because 0 can be written as A into 0. So therefore A divides 0. Now here 1 divides A. 1 can be written as A can be written as 1 into A. So this implies 1 divides A. 1 divides any integer, and finally A divides A because A can be written as again in the same form A into 1. So this implies A divides A. So this proves the first part, and A divides 1 if and only if A is equal to plus or minus 1. So here we can write 1 is equal to AC. If A divides 1, then this implies 1 is equal to AC, and if 1 is equal to AC, A and C are integer, then this implies A is equal to C is equal to 1, or A is equal to C is equal to minus 1. That means A is equal to C, either 1 or minus 1. A is equal to plus 1 or A is equal to minus 1. So the first two are simple, follows by the definition, or we may consider this as proof for first and proof for second. So this is two-way. So thus this implies and implied by A is equal to plus minus 1 by the definition. Now the third you can consider, if A divides B and C divides D. So third result we shall do. A divides B and C divides D. You should check according to the definition. Now what this implies? See, this implies A divides B, we write we apply the definition directly, but C is used here, so we don't use C, we shall use another letter as X. So this implies B is equal to AX and A into X, and here B is equal to C into Y for some X and Y, for some integers X and Y. Finally, what we want to show is AC divides BD, and thus we shall form the product BD and show that AC is a factor of BD. Here AC divides BD or AC is factor of BD or AC is divisor of BD, and thus we want BD. So this implies B into D. So what is the B into D from this? You see, it is AX into C1. Or this can be written as AC into XY. And you see, X is integer, Y is integer, XY is integer. So thus BD is written as AC into some integer, and this implies AC divides BD by this definition. If B is A into C for some C, then A divides B. So this implies AC divides BD. Third result. And fourth result, if A divides B and B divides C, then A divides C. First integer divides second, second divides third, then first divides third also. So that is also simple. A divides C, the fourth result. A divides B and B divides C. So this implies B is equal to AX and C is equal to BY for some XY, for some integers X and Y. And thus this will imply, now we want to write A divides, we want to prove A divides C, so therefore write the expression for C. So C is equal to B into Y. B, but B, what is B? B is AX. So C is equal to BY, and that is AX into Y, or that is A into XY. And thus A is a factor of C, that means A divides C. So thus the fourth result is also proved. Now the fifth, A divides B and B divides A. They both divide each other. Then they must be equal, or there is negative sign. A is equal to B or A is equal to minus B. That is the fifth result. A divides B and B divides A. So what this implies? B is equal to AX and A is equal to BY. We are only applying this definition for some integers X and Y. And now you see, what we have to show is relation between A and B. So we may write A is equal to BY. This implies A is equal to BY, and again what is B? B is AX. So AXY. A is equal to AXY. Now we can divide both sides by A, first and last. So what this gives? 1 is equal to X into Y. And because X and Y are integers, possibilities for X and Y are either 1 or both equal to 1 or both equal to minus 1. This implies X is equal to Y is equal to 1, or X is equal to Y is equal to minus 1. 1 into 1 or minus 1 into minus 1. And thus the value of X is 1 or X is minus 1. And from this A is equal to BY, this implies A is equal to B into Y. Y is plus 1 or minus 1, that is plus or minus 1. And thus this proves the fifth result. So this is if and only if. We can write if and only if. Two-way implication. Now the sixth is if A divides B. If A divides B and B is not 0. B not equal to 0. This implies B is equal to A into X for some X, for some integer X. And now what we have to consider is the absolute value of this. So this implies absolute value of B is equal to absolute value of A into absolute value of mod A into mod X. And now you see mod X is greater than or equal to 0, and therefore this integer and again it cannot be 0 because b is positive. Therefore, mod x must be greater than or equal to 1. So, where mod x is greater than or equal to 1, since b is not 0. b is not equal to 0, so x cannot be 0. And if x is not 0, mod x will be greater than or equal to 1. And thus, if you consider this is greater than or equal to 1, this shows that mod a is less than or equal to mod b. And thus, or we may consider from this. This implies multiply this both side by mod a, or this relation mod a into mod x is greater than or equal to 1 into mod a. And what is mod a into mod x? That is mod b. So this implies mod b is greater than or equal to mod a. Or in reverse way, mod a is less than or equal to mod b. So this proves the sixth result. Now the seventh, last one. So simple results are these, and we have to prove this by using the definition of divisibility only. Now what the last result says, a divides b and a divides c. Then a divides bx plus cy. And what is bx plus cy is called a combination of b and c, where x and y are integers. A divides b and a divides c. So apply the definition of divisibility. A divides b means b is equal to a into x and c is equal to a into y for some integers. For some integers x and y. And now you see what finally we want to show is bx plus cy, combination of this. So x and y are used, and therefore we should use another letters, because here x and y are used, and instead of x and y we shall consider r and s. So b is equal to ar and c is equal to as for some r integers r and s. Any letters can be used. Why we have changed? Because here it is x and y given in the result. And now for any integers x and y, what is the bx plus cy we should write? We want to show the divisibility relation. So therefore this we have to consider. And then show that this is a factor, a is factor of this. For any integer x and y, bx plus cy is equal to multiply b by x. So bx will be arx and cy, multiply this by y, asy. And now you see a can be taken common. So this is equal to a into rx plus sy. So this is bx plus cy. And this shows that bx plus cy has a as a factor. Therefore a divides bx plus cy. So this implies a divides bx plus cy. And this proves the last result also. So thus we have proved all the results here. Now we shall study first. We want to study greatest common divisor. Before that, we shall study common divisor. We write as a definition. If a and b are any integers, then an integer b is said to be a common divisor. Common divisor of a and b. If b divides a and D divides B. D divides A and D divides B. Then D is a common divisor of A and B. The meaning is simple. You see, 2 divides 6, 2 divides 10. So 2 is a common divisor of 6 and 10, two integers. Now we shall consider next definition for greatest common divisor. Let A and B be two integers. Two integers, at least one of them is non-zero. At least one of them, or both not zero. At least one of them is non-zero. Then a positive integer b is called the greatest common divisor. Greatest common divisor of A and B, denoted by GCD. In short, greatest common divisor of AB if the following holds, or you just say if first condition, if the following holds, or if first D divides A and D divides B. Second, if C divides A and C divides B, then D divides C. Or here we should have C divides D. Yes. D is the greatest. C divides D. Now there are two common divisor. The meaning is it divides both. And now what is the greatest common divisor? Greatest common divisor of A and B. That is GCD of A and B. So it is first a common divisor. First condition is D divides A and D divides B. So it is common divisor first. And what the second says, it is the greatest common divisor. Greatest common divisor. Now C divides A and C divides B. Means C is a common divisor. Then that common divisor divides the greatest common divisor. So that common divisor divides B, means B is the greatest. So two properties are, first it is a common divisor and the second it is greatest common divisor. Now we shall consider an example. For example, see the GCD of minus 12 and 30. Now what will be the GCD of minus 12 and 30? Now you should remember that for greatest common divisor it is positive always. Though the integer may be positive or negative, the divisors are to be considered as positive. Now what are the common divisors of minus 12? Divisors of minus 12 or divisors of minus 12 are, now we know these are plus minus 1. If 1 is divisor, then its negative is also divisor. So 2. So only we consider positive divisors. Positive divisors of this are 1, 2, 3, then 4, and then 6, and then 12 itself. 12 divides 12. So positive divisors of minus 12. So what are positive divisors of 30 are positive divisors of 30. So 1, 2, 3, 4 is not, 5, 6, then after 6, I see 15 and 30 itself, which 8. Yes. So these are the divisors. And what are the common divisors? You can see the common divisors are these 1, 2, 3, 4 and 6. And therefore the greatest common divisor is 6. Therefore GCD of minus 12 and 30 is 6. So in this way we have considered the positive divisors, and the greatest among these is 6. Now if you consider GCD of say minus 8 and minus any number can be considered, minus say 24. Now obviously it is 8 because 8 divides 24, and therefore the greatest common divisor is 8. Now what we will further see is that or you may see GCD of 3 and minus 5. Now what is the greatest common divisor of 3 and minus 5? Now the divisors of 3 are 1 and 3 only, positive divisors. Divisors of positive divisors of minus 5 are 1 and 5. So therefore the greatest is only 1. So this may happen. No other common divisor is there. And thus now one more property of the greatest common divisor is the greatest common divisor can be expressed as a combination of the two integers. Now you see the first GCD of minus 12 and 30 is 6. So GCD minus 12, 30 is equal to 6. Now how to write 6 in the combination of minus 12 and 30? Now this can be written as minus 12 into say 2 and plus 30 into 1. So 30 minus 24, that is 6. So that means GCD of GCD of A and B is D. Suppose that GCD is D. It is written as A into X. X is 2 and Y is 1. AX plus BY. This is called linear combination of A and B. And this is property of greatest common divisor. Greatest common divisor can be written as linear combination of the two integers. Now you may verify this property that GCD of minus 12 and 30 is this one. D divides A, D divides 6 divides 12, minus 12, 6 divides 30. And C divides A, if C divides A and C divides B, then C divides B. Consider any other divisor or 3. See, 3 divides 12 and minus 12, 3 divides 30. But that 3 also divides 6. C divides D. The property of GCD is satisfied by this definition. So these and furthermore, the GCD is written as linear combination of the original numbers. 6 is written as combination of minus 12 and 30. Now this is a theorem actually. The GCD of two integers is a linear combination of the two integers. And we shall prove that theorem in the